Thank you very much, Torben, for handing over, and a warm welcome from my side as well. My name is Michael Reitz, and I'm Technology Manager for the Global Technology Basis Petrochemicals from BASF-SE. And in my role, I'm responsible for the global steam crackers of the BASF and for the development and demonstration of the e-furnace technology. And today I have the pleasure to give you additional insights into our first operating phase of the e-furnace demonstration plant. So Torben already gave you some information on the plant and on the layout, on the two different heating concepts, and I will now go on with the architecture of our demonstration plant. Heart of the demonstration plant are the two furnace boxes for the direct and the indirect heating technology. Both boxes or concepts are equipped with electrical preheating for the preheating of the steam and for pre- and mixed feed superheating. Both technologies are equipped with crack gas cooling as well. As Torben already said, the demonstration plant is fully integrated into one of our steam crackers at Ludwigshafen site here in Germany, which means that all the feedstocks and utilities are supplied by this existing cracker, and the crack gas produced within the e-furnace technology is led to the crack gas separation in an existing cracker, producing high-value chemicals, commercial products already with a reduced carbon footprint, and already, even if we do not have fully heat integrated state here, we see carbon savings on scope 1 in the range of 90%. In total, the concept is heated with 6 megawatts of electrical power for the preheat and cracking reaction, so for both furnaces, and in total we are processing 4 tons of naphtha an hour in the two separate independently operating trains. I will now come to the operating performance of that system. So we kept the process temperatures or the process conditions close to conventional fired furnaces. This is mainly due to the used feed that we have here. So we utilize a full range naphtha, and therefore cracking reaction are quite described well, and the parameter range is quite known. So we are operating close to that conditions. So far, we had both heating systems in stable operation, and we were able to produce several thousand hours of incident-free cracking operation, and we produced a few thousand tons of high-value product with a reduced product carbon footprint, as I said, in the range of 90% already for the demonstration plant. And the crack gas composition that we have achieved so far from both technologies is totally in line with the design specifications. And you see an example on the right-hand side for lump components for a full range naphtha that was utilized. Therefore, and you see some small differences which are an effect of the slight difference in operating parameters for those two cases here, but in general we see similar results for both technologies. Key features of the e-furnace demonstration plant so far is that we really see a stable and accurate heat and temperature control for the both furnace systems, which means we have a homogeneous heat distribution with no hotspots, not on the direct heating elements or on the direct coils, on the direct heating coils, or on the indirect heating elements. Further, we have the possibility to have a fully remote rapid furnace heat up and feed in, which means that start of the coil heating and putting the feed into the system is entirely possible from the control room, and there is no really feed operator action required for those tasks. We see that system reacts quite robust and safe in case of trip situations. So at the beginning we had some minor trip situations, mainly caused by instrumentation errors, but we see that we have a really very robust system that could be brought back to operation by the operators quite fast, even it's a brand new technology, so to say. And the electrical heating infrastructure, which means the electrical switchgear, the transformers, the thyristors, everything which is required to power the system up is in operation as per design. We will now have a look on the specific characteristics. So we'll start with the direct electrical heating technology. So we see here a very uniform heat input into the cracking coils with a homogeneous heat flux into the process. And those conditions are really beneficial for optimized yield and reduced coking in long-term operation. We see very even heat distribution, so the temperature differences between corresponding coil segments of our multiple coil arrangement within this plant is in the range of plus minus 5%. And we see that the operating parameter variations can be implemented very fast due to the low thermal mass or inertia of this direct electrical heating system. And in the graph, for example, you see comparison of the tube metal temperature of corresponding coil segments. So you see at the upper part, there is the temperature of this coil segment, the min, and max value of those, and you see it's quite close together. And even we did a step test there, you see that as well, and even there it stays quite compact, and this is a duration of approximately 10 days that is displayed here. And on the lower picture, you see the normalized values, and there you can see that even in those transitional phases, the system reacts quite smooth and the values are kept quite constant. I will now go on with the indirect electrical heating technology. So here we can definitely state that the performance of the heating elements totally meet the design specifications in terms of heating element temperature, in terms of power consumption. And here we have a very even power distribution of the heating modules over the full height of the furnace. And we see that variation in power consumption between the different heating zones is maximum in a range of plus minus 2%. And this even power distribution also results in homogeneous temperature profiles on the coils, which are again likely beneficial for optimized yield and longer run times of such a furnace system. On the right-hand side, you see here the power consumption for the heating zones. Again, the min, max, and mean value, you see there is some fluctuations in it, but if you look at the normalized power, you see this is working quite constant, and the fluctuations are more or less due to surrounding effects, and there might be some optimization potential, or there will be by further trimming the P&ID parameters of the whole system. But if that's the only case that is required for that new technology, then we are quite lucky to have that in that way. Another electrical heaters that are implemented are the mixed and steam pre- and superheaters for the feedstock. And we can also state here that we have excellent operability and controllability of those different heaters that are arranged in the plant. And we have quite a fast response to variations from the process in terms of temperature changes, flow rate changes, or the inlet composition. And for the e-furnace demonstration plant, there is a totally new developed concept in place for the feed evaporation. And we can also state that this is working quite stable and robust. So far, we have done some variation of operating parameters, which is mainly tuning of the heat flux profile for the direct and indirect heating technologies. So both technologies offer possibilities to trim the heat fluxes, maybe in a range that is a little bit larger compared to conventional fire technologies. And currently under investigation, there's a lot to investigate with such a new technology, but for example, is the coil inlet and outlet temperature, feedstock composition, steam to hydrocarbon ratio, and the cracking severity, which is mainly done by varying residence times and the coil outlet temperature. And on the right-hand side in the diagrams, you see the dynamic response of the system. So this is the coil outlet temperature variation of the indirect furnace at the top. So we did a step change. This is the blue curve that you see, and then there's the answer from the system in terms of the heat duty, which is the yellow curve. And then you see that it was a short delay due to the heat transfer by radiation. Then the measured outlet temperature is rising as well. And at the bottom diagram, you see that for the direct, so there is a two-step change, and you see quite the dynamic response of the system, which is a little bit more direct and a little bit more faster based on the heating technology. There's not only cracking operation in steam crackers, there's also decoking and the switch over between those two. And within the e-furnace demonstration plant, we clearly could show to successfully decoke both furnaces. So we had scheduled decokings for both furnaces, and we could show that electrical heated decoking is technically feasible and that efficient decoking is feasible in that manner. And we did that by monitoring the coil pressure levels and decoking gas composition like CO and CO2, which is, I think, well known from conventional fire technology. And then we have an automated switchover procedure in place between the cracking and the decoking and vice versa, which was successfully demonstrated as well. And on the graph on the right-hand side, you see this automated switchover procedure. So the yellow line is the cracked gas valve that is closing, the decoking gas valve simultaneously open in a certain manner, and then you see the transition and pressure level with a little bit of fluctuations in there, which might be further minimized by controller optimization. Having that said, I will come to the status and next steps. It's not everything is about the technology. I mean, there are people that have to work with those technologies, the operators, and there we get a lot of positive feedback on the eFurnace technology, on the operability of our demonstration plant. So the furnace and the auxiliaries are considered easy to operate, likely due to a high degree of automation that is put in there, but also what was key, I think, is to engage the people that are working, to have early involvement of shift personnel, of operators into the technology development and comprehensive training that we have performed with the operators at the end. And what is an ongoing task is the continuous evaluation of all the operational data that we are gaining from our demonstration plant. That's the main purpose here, is to further validate our simulation and models and to further optimize the technology.